In this lecture, we're going to be going through thermodynamics and biophysics. So we're first going to define what thermodynamics is, go through a definition of what a state function is versus a path function, look at the different thermodynamic potentials, and then be able to apply them to different processes in life. So what are we going to be talking about today? First of all, go through a recap of the different structure and functions of lipids and biomembranes. We're then going to take a look at thermodynamic systems, how to define a living system, whether it's open, closed, whether it exchanges matter or energy with the environment. Next, we're going to introduce the different laws of thermodynamics. There's actually four, with the first one being named the zeroth law. So we're going to go through each of those. And as we go through each of those, we're just going to define what different state functions, path functions, and thermodynamic potentials are as they become applicable to each law. So at the very end, I'll have a summary of which types of potentials are the most important to remember and how to calculate them. Finally, we're going to go through some thermodynamics of membrane transport. So first of all, with membrane transport, there's always some sort of diffusion that's taking place, and it's always trying to achieve some sort of equilibrium. So in that case, we're able to apply thermodynamics and the idea of entropy or disorder to see how we can model the different energetics of membrane transport. So we're going to take a look at some flux and force equations in irreversible processes, as well as sodium transport across the cell membrane. So let's first start off with the recap. We're going to go through lipids and biomembranes, which plays a really important role in thermodynamics and especially what we're going to be going through in this lecture. So back in the previous lecture, we talked about how phospholipids make up biomembranes. So phospholipids are essentially amphiphals. There's a hydrophobic tail region, and it's nonpolar, and there's a hydrophilic head region, which is polar. So when amphiphals or phospholipids are placed in an aqueous water environment, that means that the hydrophilic water-loving heads are going to want to interact with the water, and the hydrophobic water-fearing tails are going to want to hide away from the water. So essentially, we have a membrane being formed as the first step. We want to be able to hide the tails from the water. So there's a hydrophilic head, hydrophobic tail, core, and then another set of hydrophilic heads. But then at the very edges, there's an edge effect in that the nonpolar hydrophobic tails are still exposed to an aqueous polar environment at the edges. So naturally, the planar membrane is going to want to wrap itself into a sphere so that it merges and there are no longer any hydrophobic tails exposed to water. This means that there can be a hydrophobic core within the membrane itself, as well as a core inside the vesicle that's formed by that bilayer. Next, we talked about membrane asymmetry and the fluid mosaic model. So the first thing we mentioned was that the lipids aren't just stable where they are in the membrane. They can actually move around in the membrane, either laterally, they can rotate, and sometimes they can flip-flop to the other side. These are all really important in terms of providing function and flexibility in the membrane. So apart from that being the fluid mosaic model, there's also the presence of cholesterol that affects fluidity. So within your membrane, there are different regions of lipids, for example, over here, that might have a high concentration of proteins, cholesterol, or some other sort of substance that's specific to a function. So those areas are what we call membrane domains. They're specific in a function and they have a high concentration of a specific type of lipid, of protein, or some sort of surface attachment. So it's really important in terms of membrane asymmetry because number one, it allows for selective transport, basically allows for a concentration gradient. You have different charged ions and particles on either side because of all of these different functions on the surface of the membrane, allowing for different ions to pass or not pass. Because of this, it creates membrane potential. This means that not only an electrical gradient is created, but also a concentration gradient, which we'll also take a look at later in this lecture. The last thing that's important to know about membrane asymmetry is that because you have these different gradients and because your lipids can move around, what's on one side of the bilayer may not reflect what's on the other side of the bilayer. So always remember that both sides of the bilayer may not be exactly the same. So types of transport. Membrane transport basically can be categorized into two different types, passive or active. Passive transport doesn't require energy to move substances across, whereas active transport does. So in passive transport, it relies on what we call the second law of thermodynamics, which we'll talk about in this lecture. And it follows Fick's first law for diffusion. So basically, it's going to move from an area of high to low concentration to increase entropy. The second law of thermodynamics states that entropy is always increasing or basically disorder is always increasing in the universe. And Fick's law basically says that it'll move from an area of high concentration to low concentration. So the different types of passive transport can be simple diffusion, facilitate diffusion, filtration, or osmosis. Those are the ones we talked about. With active transport, it's a little bit different because it requires energy. It requires it to move the molecules against a concentration gradient. That's probably the most important part to understand here. It uses the metabolic energy that we have to transport molecules across the membrane, and it requires ion pumps or channels so that those specific ions can cross the membrane. Finally, for Fick's law, for passive transport, that's one of the last things we talked about and one of the most important equations leading to the Nernst-Planck equation for one diffusing ion. Basically, in this picture, if the membrane is selectively permeable to a specific type of ion like potassium, then these positively charged ions can diffuse down your concentration gradient and to the outside of the cell. So you have some potassium over here, it diffuses down outside. What happens is you have uncompensated negative charges over here from your A's. So there's a bunch of A's which are negatively charged, and you've just lost a bunch of potassium. This separation of charges is what causes the membrane potential. And remember, we have to keep in mind that it's not just an electric potential that's created, but a concentration gradient. So if we take a look at diffusion, there are two things that are happening. One, there's a concentration gradient of ions that we have to look at, governed by Fick's first law over here, and proportional to a concentration gradient over a certain distance that it travels. There's also another equation for flux based on an electric potential gradient. So then delta phi over here represents that change in potential. The Z, the F, the R, and the T are specific to us, the ion that we're looking at, where Z is equal to its ionic charge. So if you combine the two of them together, you end up with a combined version of Fick's law for passive transport that covers both the concentration gradient and the electric potential gradient. Basically, we just add them together. And here we get what's called the Nernst-Planck equation, which is commonly used in a lot of modeling applications. And we'll be taking a look at that for thermodynamics as well as bioenergetics in the next chapter. Okay, so let's get started with thermodynamic systems. We're first going to go through a quick introduction of what thermodynamics is, especially for those who haven't taken thermodynamics before. The different types of systems that we can actually take a look at, as well as how to categorize a living cell, so which system it belongs to, and then being able to define the state of a system. So what is thermodynamics? Thermodynamics is essentially, very shortly, very briefly, a science about equilibrium. It's about how systems exchange matter and energy with each other. But um, thermodynamics has actually been defined in many different ways. It's the study of the effects of work, heat, and energy on a system. It's one way of defining it. Another way is that it's a branch of physics that deals with energy and work in a system. So all of those have to deal with thermodynamics, and no matter what definition is used, thermodynamics is truly just about equilibrium, how your system is going to exchange matter and energy with other systems or with the environment. So some of the thermodynamic parameters that we have to take a look at are those that would be within a system. So if you're taking a look at a system, then you have to define the volume of the system. The system is going to have a specific temperature and also exist at a specific pressure. So then some other things you can take a look at would be concentration, viscosity for large homogeneous phases, if you are interested in that. But for us, we're going to focus on volume, temperature, and pressure and see what happens if we keep volume or any one of those parameters constant. So when we talk about thermodynamics, we can consider it in two different ways. First, whether it's equilibrium thermodynamics or whether it's non-equilibrium thermodynamics. With equilibrium thermodynamics, it means that we're trying to look at equilibrium or near equilibrium states. If we do assume that, then that means that we have linear relationships between your forces and your rates. If you're taking a look at non-equilibrium thermodynamics, then we now introduce non-linear processes where you have dissipative structures that lose energy, different types of things that go on that cause it to never be able to reach an equilibrium state or a steady state. For our purposes, we're going to be focusing more on an equilibrium state. So what are some different types of systems? First of all, a thermodynamic system is one that consists of a great number of continuously interacting particles, whether it's atoms, molecules, or chemical structures. The system is defined according to whatever problem you're considering. So if you're taking a look at an organelle as your system, then you take a look at the organelle itself and define the volume of the organelle, the pressure the organelle exists at on the inside compared to the outside, that sort of thing. You can also take a look at an entire organ or an entire organism. So then we take a look at the types of systems, and the type really just refers to how that system interacts with the environment. An isolated system cannot exchange matter or energy with the environment. So think of it as just your system is completely isolated or separated from the environment. It's just locked itself away. That means it'll just have its own matter and energy that exists within it and will never cross the barrier between inside and outside. So a closed system, even though it does sound like it's closed, it just means that it can't exchange matter, but it can exchange energy. An open system is one that can exchange both matter and energy with the environment. So these three different systems are really important to understand and know the differences between. So then if we take a look at ourselves as living systems, what would we be categorized as? Isolated, closed, or open? If we take a look at the living cell, it makes sense that we do exchange matter with the environment. We take in food, we take in energy, we also expel that energy outwards. So that means that we should be an open system. So thermodynamically, living cells are considered open systems. Cells exchange matter and energy with each other and the environment. They work to transform the chemical energy of food into the energy required for chemical bonds, muscular contractions, as well as nerve impulses. They are also in non-equilibrium states because of evolution and self-replication. So in terms of these two processes, we're either really far from equilibrium or near equilibrium, but never exactly at equilibrium. The thermodynamic laws themselves can be used to describe the transport of energy and matter in cells, but one thing is that we have to look at slow processes. If we look at a slow process, then what we can do is assume that it's really close to equilibrium and achieve some sort of steady state. And then when we take a look at these snapshots or slow processes, then we can apply thermodynamic laws, just so that we can model what's happening within our system. So now that we've kind of been able to define what thermodynamics is, as well as what a living system is categorized as an open system, and the fact that we can apply it to a living system at near equilibrium states, we now have to figure out how we can describe or define the state of a system, and that's where state functions come in, or the thermodynamic potentials. So a state function is basically a property that describes the state independent of the path it took to get to that state. So before I begin explaining what a state function is, I want to say that there are basically two types of functions that can describe the state of something: state or path functions. The state function is a property that describes the state without depending on the path that it takes, whereas the path function does depend on the path taken to get between two states. So a really good example is usually pushing something from point A to point B. If you're starting at point A and you're pushing something to get to point P, the amount of work taken to go from A to B will change depending on the path you take. If you take a really zigzag path to get from A to B, you're going to use more work because you've traveled a longer distance, and that means you're using up more energy. But it doesn't matter where the location is or the change in terms of the two different states, because you're still going from A to B. If there are any types of systems where you're just looking at what one was before to what it becomes afterwards without worrying about the actual energy in between, then the actual state is independent of the path, because point A is point A, point B is still point B. So for a process, the change in state functions only depends on the initial and final states, regardless of the path taken. So there are some thermodynamic state functions we have to be aware of. They are internal energy, Helmholtz free energy, Gibbs free energy, enthalpy, and entropy. And so essentially over here, if you take the integral of a function, of a state function, you should just be able to subtract the final state. So basically some sort of enthalpy at your second temperature minus your enthalpy at your first temperature. So it's just a change in between those two states. A path function is a property that depends on the route taken between two states. So thermodynamic path functions that we have to worry about are heat and work. So we can't say that the system has a specific amount of work under a given set of conditions. You always have to say that a certain amount of work was done to get to that specific function through a specific path. So hopefully that makes it clear what the difference is between a state and a path function. Okay, so now we're going to be talking about the different laws of thermodynamics. So the laws of thermodynamics help to characterize the evolution of a thermodynamic system using a set of fundamental physical quantities. There are actually 4 thermodynamics laws, with the first one starting from the zeroth law, and they evolve in terms of complexity and the number of state functions that are involved. So to make things easier to understand, we'll present the state and path functions relevant to each law as we go along, just so that we can build up our understanding of thermodynamics step by step. So let's start with the zeroth law of thermodynamics. Basically, it states that if two systems are in thermodynamic equilibrium with a third system, the two original systems are in thermal equilibrium with each other. So let's look at this diagram here. There are 3 systems, A, B, and C. Now, if A is in equilibrium with B, it means that there's no heat that's going to be exchanged. It's simply just going to be equilibrated, same temperature for both systems. Now, if you say that B is also in equilibrium with C, it means that B and C also can't exchange heat with each other. It's already done, they're currently in a state where the two of them are in equilibrium. And that means they also share the same temperature. So if you look at all three systems together, B cannot be the same as A without being the same as C. So therefore, all three systems, A, B, C, have to be in equilibrium with each other, especially if we talk about thermal equilibrium. So by making that connection between A and B and C, we can say that A and C are also going to be in thermal equilibrium with each other. So just keep in mind that when two systems are in thermodynamic equilibrium, they're not going to be exchanging any heat, and because of that, they will have the same temperature. Now let's take a look at an example. I'm just going to walk through it verbally. Let's say that you have two systems, system A and B. System A has 1 kilogram of water, or 1 liter of water, and it's at 10 degrees Celsius. But then system B starts off a lot larger. System B is actually 10 kilograms or 10 liters of water at 100 degrees Celsius. So just change this to 100 degrees Celsius, and the fact that it's 10 liters instead of 1 liter for A. And now we want to see what is the temperature of the water when it reaches thermal equilibrium between both systems. So in that case, we take a look at the total mass between the two systems. In this case, it would be 1 liter plus 100 liters to make 100. This one was 10 liters. So 1 liter plus 10 liters is a total of 11 liters. And then in terms of the temperature, this was 10 degrees and this was 100 degrees. Because you have 10 times 1 liter of 100 degrees, you then have 10 times 100 or 1,000 degree units. And here you have 10 degree units. So together you'd have 1,010 degrees. So essentially, I'm just trying to average them together. You average the mass and you average the temperature, and then you will be able to figure out the final weighted average of degrees per kilogram. So if you divide the total number of Celsius units by 11 liters in total, you should get 91.82 degrees Celsius at thermal equilibrium for both systems combined. So let's start with internal energy U. Is it a state function or is it a path function? Well, the internal energy describes the amount of energy that a system has under certain conditions. And that really is possible. So that makes it a state function because we can define it under a certain set of conditions. So internal energy is defined as the kinetic and potential energy associated with how molecules move in a random disordered way. It includes energy on a microscopic scale. So when we take a look at, let's say, a glass of water sitting on a table, we can't say it doesn't have energy. It actually does have energy. Even though it doesn't seem like it's moving, if we zoom in to the microscopic level, all the particles and the molecules are vibrating and moving randomly. So we have translational kinetic energy of the molecules. You have vibrational and rotational kinetic energy of those molecules as well. So this picture right here depicts that. Then over here, you also have the attractive forces in between the molecules, so like hydrogen bonds and everything, and that gives you potential energy. So within a microscopic system, there's not just kinetic energy, but also potential energy as well, and that is what defines internal energy. So now that we can understand qualitatively what internal energy is, how do we define internal energy mathematically? And so we know there's potential and kinetic energy, which means usually there's work involved. So what is work? Remember, if you're moving something from point A to point B, the work does depend on the path you take from point A to point B. So that's a path function. So in terms of taking a look at internal energy, we need to look at how much energy is added to the system, as well as how much energy or work is done by the system that's being lost. So this then leads to the first law of thermodynamics. So the first law of thermodynamics basically says your internal energy of a system is going to be equal to how much energy you add to the system in the form of heat, as well as how much energy is expended by the system, or how much work is done by the system. So that means you're removing that work from that system. So that's the first law of thermodynamics. Some considerations: isolated systems cannot exchange heat or work. So if you are in an isolated system that cannot communicate with the environment, it means that there's no heat being added in, there's no work being done. So essentially you have delta U being 0. Its initial state is equal to its final state because no change is happening. Now, because energy is conserved, if there is a change in the internal energy within your system, it means that that energy must also be reciprocated by the environment. So it has to be that the change in energy in the system is equal to and opposite to the change in energy in the environment. So these two are very important to know. Now, the last 2 points really have to do with when do we know when the change is positive or negative. Let's take a look at the positive version first. If there's energy that's entering the system, then that means we have positive Q, or positive heat, getting added to the system. And if work is done on the system, it means that W must be greater than 0. So this term is also going to be positive. So then you have Q and W both being positive, which means delta U is greater than 0. Now, if the energy leaves the system, that means delta U has to be less than 0 because the change in energy is going to be negative. That means your heat is going to be released, so you have a negative Q, and then the work is going to be done by the system, so you are going to subtract W from the system. So you have minus Q minus W essentially to give you an overall negative number. So just know what happens if delta U is negative or positive. Now, heat or Q is considered the amount of energy transferred from one system to its surroundings due to a temperature difference. So right now what we're doing is going through the first law of thermodynamics. Delta U is equal to Q minus W. Q and W are both path functions, so we're going to define those now so that we know what they are. So heat, it describes the energy transfer due to temperature differences, and it's going to go from high to low temperature. The best way to explain this is when we touch something hot or cold. When we touch something hot, energy is going to flow from the hot object into our fingers, and we perceive that incoming energy as hot because our fingers are cooler than the object. On the opposite side of things, if we're touching something cold, then that means our fingers or our hand will be at a higher temperature, and we're going to lose energy as it dissipates into the cold object, and therefore we feel cold. So what's shared between these two examples is the fact that there exists a temperature difference between our fingers and the object we're touching. And that means this is the ultimate cause of heat transfer and also a push towards equilibrium. So how can we model this mathematically? The heat is going to be proportional to a change in temperature. The greater the change in temperature, the more energy that's transferred. That makes sense. The larger your object, the more heat it can hold, and the more energy has to be transferred. So that can also be something else that heat is proportional to. So what we can say is heat is proportional to m times T, or change in T. But this is only a proportionality statement. We want to be able to make an equality or some equation out of it. So when we want to convert a proportionality to an equality, we just add a proportionality constant C. So in this case, we call that C the specific heat, or sometimes called the specific heat capacity. And you end up with this equation, Q equals mc delta T, which should be quite familiar to you if you've been taking chemistry. So the specific heat is a proportionality constant, and every object is going to have a different, or every substance is going to have a different specific heat capacity in calories per gram times Kelvin. So now on to work. We want to first define what work is and then tie it back to how we experience work in living systems, because it's only slightly different because we have to consider something else. Work, we should be quite familiar with it already. It's the energy transfer to or from an object through the application of force over a certain displacement. So right now, what I want to take a look at is the work that's done by the surrounding on the system, because it's easier to visualize. So we take a look at this, this little cylinder here that's trapping some gas or something that's compressible. There's an external force that pushes the top of that cylinder, some kind of disc, and compresses the gas. So work is usually defined by force times distance. When we're taking a look at gas, we have to define force, and force is usually related to the amount of pressure that's being applied. So force is equal to the amount of pressure being applied over a certain amount of area. So that means it's F over A. So if we take a look at the force on a gaseous volume, we can say that the pressure is equal to the force being applied over a certain area, F over A. So that means F is equal to P times A. So that means my W equals FD can be converted to W equals to PAD, whereas D is now the change in height. So we change that to delta H. Looking at this diagram here, we see that A times delta H, the change in height, is really just the volume of that purple cylinder. So we can call this delta V. So now we have a condensed version of this equation, W equals to P times delta V to get here. Now keep in mind, this is going to be the work done by the environment on the system. We now want to figure out the work done by the system to its environment. And remember, energy is conserved, so that means that the work done by the system on the surroundings is just the negative of what we just solved for. So W equals to negative P delta V. So that's the definition of work in terms of thermodynamics. If we take a look at living organisms, one important thing with living organisms is if we compress our organelles or some different or cells, then the volume doesn't really change under pressure. So we have to exclude some additional work from the internal energy that prevents this collapse from happening. So in living systems, we now have delta U is equal to Q minus W. W is now P delta V, but we also have to subtract some sort of living organism related work. So that can be mechanical work, osmotic work, electrical or chemical work that's being done inside living organisms. So there is additional work that comes not from physical force, but from biochemical reactions. So we represent that with the W prime. Now, what do we do when we apply the first law of thermodynamics? First of all, the question here is, can we apply thermodynamics to living systems? Because living systems are open systems, and it makes it really hard for them to reach equilibrium. And it's always easier to apply thermodynamics to an equilibrium or near equilibrium state. So we already discussed that we can apply thermodynamics to living systems if we assume slow processes. And if we assume slow processes, it means that your temperature, your pressure, and your volume should really be constant. So that means we have to take a look at what happens when we keep the temperature constant, keep the volume constant, and keep the pressure constant. So over here, we take a look at volume and pressure. The reason for that is because those two are things that we know living systems will not change if the process is really slow. So we take a look at what happens when you do change the temperature of a system and hold the other two constant. So if you have a changing temperature, which we can calculate with our equation for Q equals to mc delta T, what happens if we keep volume constant? If we keep the volume constant, we have delta V equals to 0. So our W equals minus P delta V is also equal to 0. This whole thing just goes to 0. That means for your internal energy, you now have QV, where the V represents holding the volume constant. QV minus W is equal to W0, so it's just equal to QV. So then delta U is equal to mc delta T, with the CV representing the specific heat capacity that exists for that substance at a constant volume. So that's just the equation for internal energy if you have constant volume and a changing temperature. Now, what happens when you have constant pressure? That means delta P is equal to 0. But taking a look at this equation, delta U equals to QP minus W, where QP is equal to mCP delta T, and W is equal to P delta V. There really is no delta P that we can look at, but there still is a changing volume. So that means we have delta U equals to mCP delta T minus P delta V. And so that CP represents specific heat capacity at constant pressure. So taking a look at this constant pressure equation, we can now try and define a new state function called enthalpy by taking advantage of what we just solved for. So enthalpy, at constant pressure for a system in equilibrium at temperature T and volume V, we now want to try to solve for QP, which is the heat transferred to the system at a constant pressure. So we're taking the equation we had from the previous slide, delta U equals to QP minus P delta V, and we're going to solve for QP. So we rearrange everything, and QP is equal to delta U plus P delta V. Now, the simplest way of explaining this is that QP can simply just be renamed enthalpy, H of the system. So our delta H is equal to QP, which is equal to delta U plus P delta V. And so that is the definition of enthalpy, which is another state function. Another thing I wanted to mention is that in practice, many physical and chemical processes take place at constant pressure. So that's why enthalpy is really important for living systems. Many chemical reactions and biological processes are going to involve experiments. So when we're doing experiments, we can easily monitor the enthalpy change because these values are easily measurable. So let's now talk about the second law of thermodynamics. Basically, this says that in a spontaneous process, the entropy of the universe increases. So now we get to talk about entropy, which is the level of disorder of a system. Now, the second law of thermodynamics has been restated or redefined in various different ways. First of all, thermodynamic processes can progress simultaneously towards the most probable state, something to do with multiplicity. The most probable state has the highest degree of disorder, and entropy can be thought of as a measure of disorder of a system. So how do we know that the most probable state is one of high disorder? First of all, we take a look at a few scenarios and we try and think of what happens in terms of whether it's high order or low order. So if you have a lot of particles, that means there are going to be more possible ways to rearrange those particles. That means that there are more states that can be created. So you can have certain molecules arranged in a certain configuration, so on and so forth. The more molecules you have, the more configurations you can have. So in that case, the more number of states equals more disorder. If you have a higher temperature, it means that there are going to be more energy states that are possible, and that leads to more disorder. If you have less structural organization, so for example, if you have a gas instead of a solid, it's going to tend towards more energy states as well. So that means there's more disorder. So in terms of the structural organization, think about it this way. If you have a solid object, there are only so many ways you can rearrange it. But if you have a liquid instead of a solid, there are many more ways where you can modify the shape. And the more ways you can modify something or have different states for that system, that creates a higher level of disorder because there are more states possible. So that can be said in general for states and how they're related to disorder. Now, entropy. Entropy is a measure of the number of microscopic ways a system can be arranged to give the same macroscopic state. So, in other words, it describes the disorder in the system and how many states are possible. The second law of thermodynamics essentially just means we're going to use entropy to assess how spontaneous a process is. So the microscopic definition of entropy is given by this. It is S equals to KB ln W, where this is the Boltzmann constant given by this value here in joules per Kelvin. W, very important to know that it is not work. It instead means it means multiplicity. It means the number of microstates that are associated with a given system. Now, in literature and also in physics, W is used for work and W is also used for multiplicity. So we're going to keep to that trend and use W for multiplicity in thermodynamics. So now we can, now that we've defined entropy, which is the state of disorder of a system, another state function, we can also look at what happens when there's a change in entropy. And with the second law of thermodynamics, the change in entropy for a spontaneous process usually should be negative because it usually should be positive because as your system grows or as time progresses, your entropy should be increasing. So basically the level of disorder is going to increase as time progresses. So to define delta S, when a system receives an amount of energy at a constant temperature T, the entropy change is defined as delta Q divided by T. So how are these changes taking place? Number one, we have to assume that the changes take place very slowly over a long period of time, which means that we've applied thermodynamics to a system that's near equilibrium or is in a reversible condition. If there is a reversible process, the entropy change is going to be zero because it goes from A to B back to A. If it's an irreversible process, the entropy should increase because of the second law of thermodynamics. So one of the key things is if you are looking at a living system and a natural phenomena, they're all irreversible because we can never be at equilibrium. But we can approximate things as reversible if changes are small and processes are slow. So that's exactly what we'll do for the rest of this lecture. So we redefine delta S using Q rev to represent how we're going to apply entropy in reversible processes. So the heat exchange for a reversible process is delta Q rev. So delta S is equal to delta Q rev divided by T. So that's just very simple rewriting of definition of delta S. We now want to consider what happens when the heat flows between two objects, or the system versus the environment, with different temperatures. And we're going to assume that the system is hotter. So if we consider the heat flow, only three possible things can happen. Option one, the heat is going to flow from the hotter to the cooler object. Option two, the heat's going to flow from the cooler to the hotter object. And option three, the heat flow is reversible. And that is like an ideal solution. So let's go with option one first. In terms of the first law of thermodynamics, we know that energy is going to flow from a higher temperature to a lower temperature. So option one seems to make more sense. And that means that it's going to be a preferred reaction, so it should be spontaneous. So that means if it's spontaneous, you have delta S cis. So the system itself, it's going to experience minus Q rev divided by T cis. So over here, you do have a negative, you have a loss of heat from the system, but in the environment, you're gaining heat. So in this case, if you add the two up, you should end up with delta cis plus delta S, but it is a spontaneous process, so that means that this is going to be of a higher, delta S environment is going to be of a higher value, so that means it's going to be greater than 0. With option 2, the magnitude of the entropy change for the surroundings will again be greater than that of the system, but in this case, the signs of the heat changes will yield a negative value for your delta S universe. So that's the total of both of them together. So this process will involve a decrease in the entropy of the universe. Option 3, we have heat flow is reversible if the temperature of the system is approximately equal to the temperature of the environment. In this case, it's ideal and reversible. Basically, the two are going to be exactly identical, and therefore it's going to be equal to 0. So just keep in mind, the main differences between the two of these is the temperature of the system and the temperature of the environment. Because I've stated the temperature of the system is hotter, the denominator here is going to be greater in both cases. So your delta S cis is going to have a smaller impact on your overall delta S. Now, taking a look at entropy in isolated versus open systems, for a reversible process, the changes in entropy can be divided into two different types. It can be entropy production within the system, which we call an internal change in the entropy, and there can be an entropy exchange between the system and the environment, which we call an external or environmental change in entropy. An isolated system, we know, doesn't exchange matter or energy, so it's adiabatic. That means delta Q is equal to 0. The entropy law for an isolated system is then given by just internal change in energy is greater than 0 for all reactions taking place inside. That will always tend towards greater entropy. And then with the environment, there will be no change in entropy because there's no communication between the isolated system and the environment. So that change is going to be 0. So real spontaneous processes that are in the isolated systems themselves will increase in entropy. Now, what happens if we have a living open system that's not in equilibrium? So that means your delta S total should really be increasing overall once you add everything up. If we assume a steady state, it means that the internal change in entropy is equal to the external change in entropy. So this means that delta S total equals to 0. That's what happens if we can assume a steady state. So now, biological systems, we know, are considered open systems. And we want to take a look at how it exchanges matter and energy in the environment. So taking a look at this diagram, biological systems take something that's disordered and bring it into something that's more ordered. You have energy going into plants, into the leaves, and then through the chloroplast, we create sugars, which are highly organized structures. So in this case, it's the opposite of what we just said. With the second law of thermodynamics, the universe tends towards entropy, a higher state of disorder. Why is everything the opposite when we're looking at biological systems? We actually take things and make them more ordered. So the most important thing here is that for living systems, we take in a lot of energy. And so order or life can be produced when energy is supplied to us. So plants are going to use energy from the sun in the chloroplast, which are going to produce ordered sugar molecules through photosynthesis. Animals are then going to use mitochondria to convert stored glucose energy into the energy we need to form more highly ordered structures. So we'll be talking about that in the next chapter for bioenergetics. So then the last law of thermodynamics, the third law, it states that the entropy of a pure crystalline substance at absolute zero is exactly zero. So why can this be? So at absolute zero, we assume that everything is still. We know that entropy is defined as Kb ln W. So if you have a pure crystalline substance at absolute zero, it really should have only one possible structure. And if it only has one possible structure, it means that it only has a multiplicity or a disorder of 1. That means there's only one state that's possible. So if W is equal to 1, then ln of 1 is equal to 0, so then your whole term for S becomes 0. This means that there is only one possible state in which the crystalline structure exists. And as temperatures increase, the molecules are going to start moving a little bit more, and the number of states is going to increase. So therefore, the third law of thermodynamics simply states that the entropy is going to be 0 for a crystalline substance that's pure and exactly at absolute 0. So now let's talk about thermodynamic potentials. There are 4 thermodynamic potentials that are useful in chemical thermodynamics of reactions and non-cyclic processes. So just keep in mind, we already finished all of the laws of thermodynamics. Now we want to take a look at potentials which really have to do with chemical reactions. And so there are 4 we have to know about. Internal energy and enthalpy we already covered, and we know that in order to get enthalpy, it's just U plus PV. So H is equal to U plus PV, and that was the equation we derived before. We also, we didn't touch on F and G, where F is Helmholtz free energy. It's what's called the measure of the amount of energy that has to be put into a system to create a system apart from spontaneous energy transfer. So essentially, Helmholtz free energy is just the internal energy minus the entropy of spontaneous energy. Then you have G, which is Gibbs free energy. And Gibbs free energy is quite important and something that a lot of chemists and biochemists and scientists use to study chemical reactions. Gibbs free energy, G, is the maximum amount of work that can be obtained from a reaction. If we want the maximum amount of work that can be obtained from a reaction, we really need to have all of these combined into one. So G is equal to the amount of enthalpy, which is derived from U plus PV. And then we have to consider Helmholtz free energy, which is the amount of energy that has to be put in to create a system. So we then have G. In order to get to G, we have U minus TS to get to F, and then plus PV to get to G. Or you can have U plus PV minus TS to get to G. So this chart here helps you derive all of the equations required for U, F, H, and G. So focusing a little bit more on Gibbs free energy, biological systems are what we call open systems, and they're in equilibrium with the environment. So usually we have a constant temperature and a pressure such that there's no net change. If you have a non-equilibrium process at constant T and P that are described by Gibbs free energy, you have delta G. We usually just call that free energy. Basically, it means we know we have a non-equilibrium process, but there has to be some sort of measurement of the amount of energy within that system. So we're going to use that equation that we had before from the thermodynamic potentials slide. Delta G is equal to delta U plus P naught delta V minus T naught delta S system. So the naught just means the starting pressure or temperature. If we have a negative value of delta G, that means it's decreasing, then we know that the forward reaction is spontaneous. The reason for that is because that means this term, the delta S, should be increasing to make this more negative. If delta G is equal to 0, then that means the system is at equilibrium. There's no change in entropy or anything else. If delta G is greater than 0, it means that the effect of this negative term, the entropy, is going to be smaller, which means two things. Either delta S is really small, or the change in entropy is very negative. To make this a positive value. So that means a negative change in entropy means something that's not spontaneous, because it means we're creating something of greater order versus disorder. So that means the forward reaction is non-spontaneous. So an example is the oxidation of glucose. Delta G is equal to 2,870 kilojoules, which is the main energy reaction in living cells. It is a value that's greater than 0, so that means the forward reaction is non-spontaneous, and that means we need energy. The last part of this lecture really has to do with the thermodynamics of membrane transport. So we're going to take everything that we've learned and try and apply that to discuss the energetics of membrane transport. So the first thing we have to do is define what an equilibrium versus a steady state is, because the steady state is really important for us to make measurements and equations out of. We have to define the chemical potential, then take a look at the thermodynamic analysis of simple diffusion, and then some other equations to represent the flux of flow, because we are talking about diffusion for irreversible processes. Then we take a look at sodium transport across the cell membrane. So just remember that the system is at equilibrium when delta G equals to 0. So just keep that in mind. It means that delta G is going to be related to some sort of equilibrium constant K. So since we know delta G is equal to 0 at equilibrium, there exists an equilibrium constant K to make that happen. So the standard free energy, delta G prime, is usually directly linked to the equilibrium constant KEQ. We define delta G as negative RT ln of K, where K is defined as this. There's just another way of representing that. Just keep in mind that delta G with the circle degree sign, delta G prime, is usually referred to the standard free energy. And it's really important to note that reaction spontaneity is not decided by that standard free energy. It's decided by delta G. Now, the steady state versus equilibrium is in non-equilibrium, where delta S is at a minimum. So even though we can say a living system approaches equilibrium, we can say that a living system is going to be in non-equilibrium, but have a steady state where delta S is minimized. So that means your delta cis over time equals to delta G over time equals delta T over time. All of these changes are at a minimum. Now, chemical potential mu, over here, it's a measure of how much free energy, how much of the system's free energy changes because of a change in the number of moles of particles. So therefore you have delta G over delta N. We have a change in free energy over a change in the number of molecules, so that would be a chemical potential. Of course, we assume that P and T are constant, so we have this T saying that it's all at the same temperature. Now, the particle species, I, right here, can be atoms and molecules, but in solid state physics, this can be electrons and holes called fermions, in which case the chemical potential is called Fermi energy. Now that we kind of know what chemical potential is, we want to apply that to different systems. For a single component system, the chemical potential is free energy per mole. So you have delta G equals to mu times delta N, or G equals to mu N. If you have a multi-component system, then you have a bunch of these added together. So you have delta G total equals to the sum of mu I times delta Ni. If you have a mixture of ideal gases and solutions, then we have to introduce another component or parameter, and we call it mu naught I. And so that is going to be the standard reference potential. You have the same equation for G over here, but you have to add a starting point for where that potential is. So the substances that exist in two phases, A and B, are usually represented by mu I equals to mu IA minus mu IB, which is equal to RT times ln of a concentration gradient. So we can have a concentration gradient of a specific ion or substance that we're looking at in the first phase, and then the concentration of that in the second phase. Oops. Now we're going to be able to approach membrane transport with a little bit more knowledge of thermodynamics. Remember, a cell is an open system and it has to interact with its surrounding. Simple diffusion is a non-interacting component. Facilitated diffusion occurs with the help of carriers and channels. So we're going to first take a look at simple diffusion and then take a look at facilitated diffusion, which is a little bit more complex. Simple diffusion can be explained through a very simple model. You have two aqueous phases, A and B. They're separated by a semi-permeable membrane. Several types of particles can move through this membrane, but others cannot. The whole system is closed. There's no matter exchange between the system and the environment, but there are basically two phases within that system. So it does exchange, it's a closed system. It doesn't exchange any energy from the outside, but it does exchange from the inside in terms of heat and energy. So here's a picture of the two phases within that system. For simple diffusion, we can model the total entropy change during membrane transport as the sum of change in both systems. So the total entropy change over a specific amount of time is equal to the change from A plus the change from B over a certain amount of time. If we assume that the entire system A plus B is near equilibrium, then technically these two are already close to each other. So ln of A, or not ln of A, in A, you have T delta S of A is equal to delta UA plus P delta V minus this. So it's important that we have this term for chemical potential in here as well. In B, you have T delta SB is equal to the usual minus the chemical potential, total chemical potential of any ions in B. The net entropy change is then a sum of the internal and external entropy changes. So basically we have to add those two together. In a closed system, only heat is exchanged with the environment. So we basically have T delta ES is equal to delta QA plus delta QB. Meanwhile, the total internal energy change for both phases is delta UA plus delta UB. And then we just add all of these together that we had before, and we have heat plus work, basically. What we want to do is combine it all to get internal entropy production. So let me just go back. Between these two equations that we have for T delta S, the fact that we can just say T delta S is equal to delta Q plus delta QB, and the fact that we have delta UA plus delta UB, we can combine all of it to get delta S over delta T, where we have 1 over T, and we have all of this rewritten so that you have the sum of the chemical potentials for the two phases. Now, taking a look at the previous equation, there's particle exchange between A and B. So if there's particle exchange between A and B, it means that the change in the in the number of molecules of a certain ion, let's say I, or a particle, is going to be positive for one phase and it's going to be negative for another phase. And that change, we can consider the flux So therefore, delta IS divided by delta T is equal to 1 over T, and we have the sum of the flux of the diffusion of those molecules. So we say the flux of the ith type of particle is given by J is equal to delta N over delta T. So going up here, this equation, we now want to replace the chemical potential with some sort of flux, and that's going to lead us to some flux equations. So we now have J is equal to delta N over delta T. We want to introduce something else called the thermodynamic force, X. It's given by the chemical potential difference, which is delta mu I. So you now have J times delta mu, and delta mu can be represented by xi. So therefore, I can just say the entropy change is then T delta S over delta T is equal to the summation of my thermodynamic force multiplied by my flux. So hopefully that gives you a brief overview of the different equations that we can use to represent entropy change in simple diffusion. Now for facilitated diffusion. It's a little bit more complicated and it's more of an advanced model. Facilitated diffusion assumes that the interaction of a transported substance S meets with a carrier C. So we have to consider a chemical reaction in which S is added to C. So we have essentially S plus C is equal to CS. And then later on, it can become two separate items again, and then C can transfer over. So in facilitated diffusion, your substance has to bind with a carrier, and that carrier is going to help that substance across, so it's going to combine as one, and then in the second area, it's going to release that substance so it can continue through. So looking at this, there are several membranes involved, or barriers. We have 1, 2, 3 as the 3 different barriers. 1 and 2 are going to be permeable to S, but 2 is not. 1 and 2 are permeable to S, but 3 is not. So what happens here is 2 is permeable to the carrier C and the complex SC with a permeability of P. That's what we can assume. Substance S cannot go through 2 by itself, as a concentration of S out is greater than S in is necessary for passive transport. So if you have none of it here and some of it here, then basically that passive transport will not take place. Now, in near equilibrium conditions, the flux CS from A to B is going to be given as follows: some permeability constant multiplied by concentration gradient, or change in the concentration. It's going to be equal to negative JC, which is equal to negative P delta C. Now, the flux of S across all membranes, you now have to take a look at each one separately and add them all up. It's going to be JS is equal to PKC S naught minus SI divided by K plus S naught minus SI. So this is something that you'll be asked to explain as part of an assignment. So you can take a look at that for some additional information as to what's involved in every step of the process. Now K, the equilibrium constant, is going to be equal to CS over the concentration of the combined complex CS. Now we take a look at different equilibriums. So what we're going to do is just present you with several different equilibria that you should be familiar with. There's something called a simple phase equilibrium. So that's an attempt between two phases to reach equilibrium in a simple fashion. So in simple phase equilibrium, you have an ion or a solute or a particle that's called I. It is going to go through a semi-permeable membrane. It's a one-component system. You have ith type particles that go through the membrane because of a concentration gradient. You have the concentration of the ion being greater in A and smaller in B, so I is going to naturally go towards phase B to try and reach equilibrium. In that case, if n moles diffuse through, the free energy change in the combined system is delta G equals to what goes out of A comes into N. So essentially, you have delta G equals to 0, and mu IA is equal to mu IB. Next, we have osmotic flux equilibrium. There are two components now. There is a solvent S and a solute I, where S molecules are going to go through the membrane through some sort of gradient, and the membrane driving force is going to be the concentration gradient of solute I. So here I have a greater concentration of solute I here and less over here. And so there's going to be a greater push for solvent or the liquid to move into B so that the concentration of I is reduced based on the amount of solvent there is. So once again, you now have mu SA equals to mu SB to reach equilibrium. The next type of equilibrium we want to talk about is electrochemical equilibrium. In electrochemical equilibrium, an electrolyte like sodium chloride is in different concentrations in A and B. In the case of sodium chloride, your sodium ions, which are positive, we can assume that there's more sodium ions in A than in B, so that means that your sodium ions will try and move towards B. However, Cl is not going to move. What happens here is that it's going to create an excess of cations and anions on either side of the membrane, and therefore that causes some sort of effort to equilibrate between the two phases. The Donnan equilibrium explains the behavior of charged particles near a semi-permeable membrane. So this is our semi-permeable membrane. What happens here is, let's say you have some potassium outside in the extracellular matrix, and you have some negatively charged chlorine ions. You also have potassium here and chlorine ions here. Now, there are more positive potassium ions than outside, so naturally they're going to want to go out. Meanwhile, you have chlorine, which wants to go in. So that, based on an ion gradient or concentration gradient, is going to allow for the diffusion of the ions from one side to the other. But what happens if you have the existence of some charged proteins that are too large to go through the membrane? That means you're going to permanently have some sort of unmovable charge on one side of the membrane, and that causes an imbalance. So there are some particles that fail to distribute evenly across the two sides of the membrane, like large proteins or ions that just can't move across. In that case, it leads to an electric charge and an electrostatic potential between the two membranes. So some important properties of the Donnan equilibrium. All it's saying is that there is an equilibrium of ions, but the presence of large objects is still going to create a non-equilibrium and an equal electric charge. So the Donnan equilibrium, some important facts to remember. It says that both phases are electrically neutral, but the concentration of different mobile ions are different in different phases. There are immobile and heavily charged particles, like proteins, that stay inside the cell and indirectly affect the distribution of mobile ions. So that explains the Donnan equilibrium. So now we want to take a quick look at irreversible thermodynamics. Remember, a biological system is an open, non-equilibrium system. It's going to be one that interacts with the environment by exchanging matter and energy. So we want to consider near equilibrium in a steady state. In general, the change of a thermodynamic parameter with time is called the thermodynamic flux. And this is caused by some sort of thermodynamic force X. So we talked about these before. So that thermodynamic flux being caused by a force X needs to be related by some sort of proportionality constant. We call that L. So now we have J equals to Lx. And in terms of what systems we look at, we have to be able to define L differently. So in general, at near equilibrium states, the flux Jk of the kth irreversible process is linearly proportional to the conjugate force xk. So it might be a little bit complicated to explain. Simply put, if you have an irreversible process that's called K, then the flux for that irreversible process is equal to some sort of constant based on that irreversible process multiplied by the thermodynamic force experienced by that process. We're going to take a little bit of a deeper look into this. If we have a diffusing particle that's polar, which means that there are ions involved, the diffusion flux isn't just going to be caused by a concentration gradient, but also potentially an electric potential gradient. So if we're taking a look at the particle diffusion flux, it has to depend on two forces. There's Jn for the total number of basically the concentration gradient, n, that has to do with the number of ions. So Jn is equal to ln xn plus ln xe. So E refers to the electrical gradient. Both of these numbers, lnn and lne, these constants, they're called Onsager's phenomenological coefficients, the long name, and they're independent of forces. So these are just coefficients that are being used to represent a proportionality constant for different ions and different types of gradients. In an ionic medium where there is an electric potential gradient, we now consider Len times Xn plus Lee Xe, and this gives us the electric current or charge flux, Je. So keep in mind there are now two equations. There's a flux for particle diffusion coming from two different forces, and there's now an electric flux coming from mechanical and or concentration and electrical forces. And each of them have their own proportionality constant. So there's a total of 4 proportionality constants in these two cases. So these were the two equations that are the most important for Onsager's force-flux relations. If I'm taking a look at the particle diffusion flux, Jn, we call Xn the conjugate force because it's the force that's related to the flux that we're looking at, and we call Xe the non-conjugate force because it's not related to the flux that we're looking at. So over here, Xn would be the non-conjugate force for Je, and Xe would be the conjugate force for Je. And these constants here, Onsager's constants or coefficients, they are not dependent on the forces at all. Something else I want to mention is what happens near equilibrium. Near equilibrium, the forces and the fluxes are going to be coupled in a linear fashion to give what's called Onsager's reciprocity relation. So at equilibrium, Len should be equal to Lne. So these two should be equal to each other. And these coupling coefficients between two non-conjugate forces are going to be equal. So looking at entropy production and dissipation, we did take a look at irreversible processes and how it led to an increased entropy S and a loss of free energy T delta S. The time rate of energy dissipation can be defined by what we call a dissipation function, sigma. So sigma is equal to T delta IS divided by delta T. We can also rewrite that as a summation of the flux force relationships for each particle. In an isolated thermodynamic system, we know that it has to evolve towards an equilibrium state. A living open system evolves towards a steady state. So just keep in mind the different terms. Over here, an isolated system is not ideal. An ideal is a living open system evolving towards a steady state. So that's pretty much it for entropy. I do want to take a look at applying what we know to some sort of transport across the membrane. We're definitely going to take a look at it a lot more in the next chapter. But consider the flow of sodium ions across a cell membrane. Ion transport has two driving forces, the diffusion gradient and the electrical gradient. Besides passive transport, there's also active transport coupled with chemical reactions. So there are many ways in which sodium ions can flow across the membrane. So if we're just looking at the sodium ions, the total particle flux is defined by these two equations. You have Jn, where you have Onsager's coefficient, times delta mu, minus ln r times A, where R is the reaction. The flux coming from the reaction is LRN delta mu, and then you have LRRA. So JR over here is defined as the metabolic current. So that's the rate of the chemical reaction that causes active transport. So that's just one more thing we have to add to the scenario. And it's going to be coupled to the electrochemical gradient that we looked at before. Now for a summary. What should you focus on for this chapter? Well, for these lectures, you should really focus on how to define thermodynamic systems, as well as what the difference is between state functions and path functions. Definitely know what the different state functions are, as well as which path functions there are in terms of thermodynamics. Know the 4 different thermodynamic laws and how those different state and path functions play a role in each one. And of course, we ended off with thermodynamic potentials, so definitely know how to get to those equations for F, G, H, and U. Last, we took a look at the thermodynamics of membrane transport. We took out quite a bit of stuff in that chapter. There are different types of equilibria that you should know of. So basically what happens if we're looking at simple equilibrium, osmotic flux equilibrium, the Donnan equilibrium, so on and so forth. Being able to model simple and facilitate diffusion using concentration gradients. Taking a look at the flux and force relations in irreversible processes, and of course, taking a look at sodium transport across the cell membrane. So just remember what those Onsager's relationships are and how they play a role in determining the overall flux of a system once you combine several fluxes together.